Okay, so today we're starting on the more algebra part of what we're doing. And you'll notice that in today's lesson and most of the lessons in this unit were in book 3, not in book 2 any longer. Okay, we will bounce back to book 2 for a little bit of this unit, and then there are some times where we'll go back to book 2 for the whole unit, but we'll be a little bit back and forth, and then eventually we'll be all in book 3. But tonight's assignment and the next several assignments are out of book 3, so be sure you're in the correct book, okay? So we're going to be working with algebra tiles, and you'll actually get to use them in just a little bit. But when you have algebra tiles, each one of them is named by its area. So, for example, here, this is 1, because every single side is 1. This side is 1, this side is 1, this side is 1, this side is 1. So the area is 1. Okay? These smaller rectangles are x. The dimensions on those, in every case, is x by 1. So this length is unknown to us. It's not, it's not 3, it's not 4, it's no particular length. Now, for this next one, we've got a square. This will be x squared, because the length of every side is x, the area is x times x, which is x squared. Then we have some slightly bigger ones, and for those will be y is the area. And the area is y because one side is y, and a side perpendicular to that is 1. For both of these, doesn't matter how it's turned, that area is still y. On the bigger square, each side is y, so the area is y squared, so we'll call that the y squared tile. And then for these last ones, the area of these is going to be x times y. Because the shorter side has a length of x and the longer side has a length of y. And the area of a rectangle is the base times the height, or the length times the width, either way you want to think about it. So that's going to be x times y. In the problems that we're going to do in here, we rarely use XY tiles. We just don't need them very often. So you've done some problems like these on homework, but we've never actually talked about it. It's just I relied on what you have learned from past classes. So it says, for each of the following shapes, write an expression that represents the perimeter and then simplify your expression as much as possible. So for this x tile, the longer distance is x and the shorter one is y. Or excuse me, is 1. This is the unit tile, or the 1 tile. So each of these is 1. For the y tile, the long distance is y. So those are both y. This again is our unit tile. It has an area of 1, and so each of these is 1. And then for the X tile, the longer dimension is X, and the shorter is 1. So when they ask for an expression that represents the perimeter, I'm simply going to pick a place to start, and you can pick any place that you want. I personally choose the top left-hand corner and I go clockwise. But whatever appeals to you is absolutely fine. So I'm going to start here and go around this direction. So I'm just going to write down all the things that I have. I've got x plus 1 plus y plus 1 plus an x. That gets me all the way to the end. Plus 1 on the right side. Now I'm coming back around. X plus 1 plus y plus 1 plus x plus 1. And then we're simply going to say, well, how many x's do I have? I've got 1, 2, 3, 4 x's. And we've got 2 y's. And we've got 1, 2, 3, 4, 5, 6 ones added together, so that's 6. All right, let's take a look at this one. For this tile, the long length is x, the short length is 1. Now, the question becomes, what is this distance right here? Well, since this area is 1, that means that this little piece is 1, and all these other little pieces are 1. Now this whole length was x, but we're missing this piece of it down here that is 1, so this length is x minus 1. So again, if I start in the top left-hand corner, I'm going to have 1 plus x minus 1 plus 1 plus 1 plus 1, 1, 2, 3, plus another 1 plus x. So we've got 2x. 1 minus 1 is 0, and then 1, 2, 3, 4 plus 4. Any questions about that? All right, let's do this one together, and then I'll let you do some on your own. So for the y squared, 3 of the sides are really easy. This side is y, the top is y, the bottom is y. For this little piece down here, I have to remember that this distance is x, and this whole thing is y. So what's left for this little piece out here? What would this be? The whole thing is y.
Y minus x.
Exactly right. Very good. This is y minus x. Because the whole thing was y, and this part of it was x. So if we subtract, we get the part that's left. Same thing is true when we're finding the sides of this. This side is going to be x. This side is going to be x. We know that this is 1. And we know that this whole thing is x. So what does that leave for this piece right here? X minus 1. And then each of these is 1. So again, pick a place to start. Again, if you start somewhere else and go a different direction, that's fine. So y plus x on the top, x plus 1 on the right, 1 here on the bottom, 1 here on the left, an x minus 1 on the bottom, a y minus x over here on the right side, and then 2 more y's. So we've got 1, 2, 3, 4 y's. And then for x's, we've got 1, 2, 3, then subtract 1, so that's only 2 x's. And then we've got 1, 2, 3, minus 1 is 2, so plus 2. And always when we're doing these, double check what I'm saying. Sometimes I'm thinking about something else and I add wrong. Yes, ma'am.
Wait, so for the x minus 1, like, what do we do for it on there?
What do you mean, what do we do for it?
Like, you know how there's like the second, what is it called? Perimeter? Like, we simplify all the ones?
Yeah. And so since there's a negative 1, there's 1, 2, 3 positive ones and 1 negative 1. So that makes a total of 2 positives.
Oh,
Okay? And then the same thing is true for the x's. There's 1, 2, 3 positive x's, but then this is a negative x. So you've got 3 positives and 1 negative. That makes 2 positives. Okay? All right. Please try this one on your own. Check with your neighbor. What's your question, Alexander?
This is perimeter, right?
Yeah.
So we don't need the x, y?
Well, we need to know that that's x, y to know that one side's x and the other side's y.
Do we need to put the x, y inside like?
No, no, no. We're only putting the stuff from the outside. So yeah, on perimeter, we're just adding all the side links together. All right. Please check mine. To make sure I did it correctly. That's pretty good distance on that one. So, everybody in agreement? Okay. So, when we write these things down, each of these is something that is called a term. Now, the definition of a term is this: a term is a single number or variable or the product of numbers and variables. So, for example, -12 is a term. It's just a single number. X is a term. It's just a single number. Y is a term. Any of those that you see is a term. But I can also have the product of those. So I might have 4x, or 5x rather, or -17x times y. Or 12x cubed. Right, because that's 12 times x times x times x. Okay, so single numbers or single variables or single numbers and variables multiplied together. So what things are not terms then? Well, for example, not terms. Like 7 times x minus 3. That's not a term. Because it's got a subtraction in it. So that's an example of something that's not a term. All right, so then the process of writing the expression more simply, in every case here we wrote out all of the individual parts and then we simplified that. That's called combining like terms. We gather all the x's together, we gather all the y's together, we gather all the numbers together, we combine those into a single term. So instead of having 2 individual y's, now we have 2y. That's a single term. So this has 3 terms. The 2y, the 4x, and the 6 are each individual terms. All right, we will also be dealing with positives and negatives. So the way that they do that in the actual tiles is they're different color. Okay? The way they do that, because it's too expensive to print all this in color, is the ones that are not shaded in are negative. And we'll typically put this somewhere near the problem so you can be reminded, oh yeah, the colored ones are positive, the ones that are not colored are negative. So this represents 5 because there are 5 blocks here. This represents -3 because I have 3 blocks but none of them are filled in. This would be 3x, and this would be -2y. I've got 2 y's, but neither of them is filled in, so that's negative. By the way, don't do this, but if it was like this, where this was colored in, again, don't do this, what would this be? It'd be 0.
Yeah.
Because I'd have a positive y and a negative y, and that would add up to 0. All right. So one of the things that we're going to do pretty regularly over the next month or so is use different mats for tiles. This is called an expression mat. The top part is the positive region and the bottom part is the negative region or the opposite region. So using a expression mat, there's 2 different ways you can represent -3. I can put 3 negatives in the positive region, or I can put 3 positives in the, again, you can think of it as negative, I think of it as the opposite region. So everything that's down here, you read it as the opposite. So this is the opposite of 3 positives, which would be 3 negatives. All right, I'm going to give you guys some expression mats and let you play with this a little bit. Please, when you're doing the tiles, try and keep from dropping them on the floor. They tend to get scratched pretty easily. And invariably because there's a little bit of sand or a little bit of dirt on the floor, when you pick it up, you scrape it across that and it gets scratched. Okay. So on your expression mat, go ahead and do this. Build a representation for negative 2x. There's two different ways to do it. The red side on these is the negative side. The red side is the negative side of the tiles. On your mat, please build negative 2x. The side that's not red.
This is negative 2x, so then just this. I don't have one. Or maybe, or just like this. Wait.
All right. So here's one way that you could build negative 2x. Right? You could put two negative tiles in the positive region. Or you could take those same two tiles, flip them over, and put them in the negative region. Remember, the negative region means the opposite. So the opposite of two positive x tiles would be two negative x tiles. Those two things are the same. All right. Now see if you can just build one for right now, for 3x minus negative 4. Can we do that one with you?
Yes.
Okay. So I want 3 x's. Then I want the opposite of negative 4. So I'm going to put that in the opposite region. And I'm going to put 4 negatives. That's one that allows you to do like 5 at a time, so you don't have to do individual ones. So be sure you have, we want here, those are Y's by the way, not X's, these are X's. The Y's are bigger. And we want those to all be negative. Yep. We want these to be positive. You live to be different, don't you? Four whole. Ooh. So let's talk about a different way that we could do this. Now, I want you to remember for just a second, earlier this year when we were adding and subtracting positive and negative numbers. Don't worry about writing this down, but if you had 6 minus negative 4, what is that the same thing as? 6 plus 4. So then 3x minus negative 4 is the same thing as what then? 3x plus 4. When you have minus a negative, that's the same thing as plus a positive. So another way that we could do this is we could bring all these tiles up and flip them over. And it has the same value. That makes sense to everyone? So when I bring it across that line, I have to flip them over. What if I decided to bring these x's down to the opposite region? Yeah, if I flip it over, once I bring it down, this would be 4 minus negative 3x. And what's minus negative 3x the same thing as? Plus 3x. So it still works out just fine. All right, so let's write algebraic expressions for each one of these. And let's not write out every single individual little tile. Let's go ahead and combine the like terms immediately if we can. So for this one, how many x's do I have? 2. Are they positive x's or negative? Positive. Again, so let's stop playing with the tiles for a little bit and let's try to keep them off the floor. So that's going to be 2x, and then I've got 3 negatives, so that would be 2x minus 3. For this one, students frequently are like, well, how am I supposed to write that? What I do on these always, to start with, is if it's in the negative region, I put a negative and a set of parentheses. So this would be minus. Is this a positive y or a negative y? It's a positive y tile. And these 4 unit tiles, are they positive or negative? Negative. But let's simplify that. That would be the same thing as, if I brought the y tile to the top, it would be negative y. And if I brought the 4 negative unit tiles to the top, it would be plus 4. Isabel, you look incredulous. Like you doubt me or something. It's okay. You can doubt me all you like. Yes, ma'am. Yeah. So, how I got from here to here? So, just like we did before, when we bring a tile across from one region to the other, we have to flip it over, right? So if we brought this positive tile, y tile, up to here, we'd have to flip it over and it would be now a negative y tile. And if we brought these 4 negative unit tiles to the top, they would now be 4 positive unit tiles. Okay? All right, let's try this one. So in the positive region, I've just got 3 X tiles. And then in the negative region, and I'm going to put parentheses around this, I've got, is that a positive XY or a negative XY? It's a negative XY plus 2 unit tiles. Are they positive or negative?
Negative. So those are positive.
These are positive. Now, if we were to simplify that by bringing everything to the positive region, minus a negative XY would be plus XY. And minus the positive 2 would now become minus 2. All right, let's try this one. This one's the most involved one. In the positive region, I've got 2 X's. I've got 2 positive unit tiles and 1 negative unit tile. Minus, in the negative region, I have 3 positive unit tiles. So 2 minus 1 is 1. So I've got 2x plus 1. And I'm going to subtract 3. What is 1 minus 3? Negative 2. So this simplifies to x minus 2. Don't worry about drawing this next thing for just a second. But I want to show you something. Right here, these 2 tiles, one's positive and one's negative. Together, what do they make? 0. So those zero each other out. And here, I've got a positive tile in the positive region and a positive tile in the negative region. Those add up to 0 also, don't they? And look what I'm left with. If I take those out, 2x minus 2, which is what we have here. That's an idea that we're going to make a lot of use of, that is zeroing things out to make them simpler. Any questions? Okay, you are welcome to keep the tiles on your desk for now. I think there may be some homework questions that are on them. Don't know how much time we have. Let's see, 11:37. Oh yeah, you've got over 20 minutes to work on homework. If you are finished with your tiles, please put them in the box at the back, right there behind Gwen. Well, how do you know you're finished with them if you haven't looked at the homework yet? Yeah, I said you should keep the tiles for now. You should keep the tiles for now. Sam, one more time. You should keep the tiles for now because there may be something on the homework that asks about tiles.
It's easier for me to do that kind of stuff in my head than the tiles.
You should keep the tiles for now.